work with that the assignment, so a little bit of a gimme here. For those that already passed it in, if you felt like you got it wrong and wanted to pass it in again, that's fine. So I created just a folder to contain all the files, and there's the one that I gave you, dat.csv. I copied in a stan file that I happened to have from earlier. I'm actually going to go grab the stan file that I had given you earlier. I think it was the within and or I guess I hadn't, yeah, I'd given you this earlier. It had this file, so. And if you'd watched the video, you would have seen that that's the file that does sort of, this is the file that has the model that can do correlations across more than 2 variables, which this data eventually was. So I'm going to delete that and open this up, which will open up a fresh RStudio. There's a bunch of code in here that I'm just going to delete because we're going to start fresh. So you probably want to load in the tidyverse and stan, and stan gives you a little thing that you probably want to run. I usually put that in all my stuff. I'll put a little load in library or packages to use. Put a little index. All right. Read in data. So that equals reader read dot underscore CSV2 and that dot CSV. So if we were to run this bit, it's got just one column. I don't know why I said CSV2, because it's actually just read underscore CSV. Read CSV2 is if the columns are semicolon separated, which they are not. So want read.csv. You can see that it's got the columns out okay. There's one named VIQ, one NVIQ, and one BDI. If we look at that, it's got those 3 columns. I didn't require that you guys actually visualize the data at all, but I can show you how to do that a little bit here. So we're going to use ggplot, and we could just say for each variable, we could go in and say, okay, well, let's even do it. ggplot data equals dat. Let's do a histogram of the VIQ column. So on the x-axis is VIQ plus, so run that. Oh, it's not. Mapping is the name of the argument, and AES is the name of the function. Okay. There's the VIQ data. Looks fairly normally distributed. If I wanted the NVIQ, I could put that in. And it looks pretty normally distributed. If I wanted the BDI. Now these scores, this comes from sort of a example from my domain where you've got verbal IQ, non-verbal IQ, and a depression score. BDI is a depression score. If you wanted to do the visual just for those 3 things separately, you could do it that way. If you wanted to visualize the data so that you could see all 3 distributions in one plot, that might be a little prettier. We need to reshape this to, instead of having 3 columns with each column having a name. We need to this is called wide data format. You'd want to reshape it to long data format. So we will sort of do a pipe of operations here. So we're piping dat to the gather function from tidier. And we want to gather all the columns. How does gather work again? Say question gather. It takes, the first thing is data, but that's getting passed to through the pipe. So the second thing is key and value. And those are just, you're giving it labels for the new columns that it's going to create. So it's going to take these 3 columns and turn them into 2 columns. One column is just going to contain all these numbers sort of stacked in a row. The other column is going to contain the label for the column from which the entry on that row was derived. So the key argument names the sort of the key column, the column that labels. So call it measure, or I guess yeah, and value column equals scale. Maybe these are 3 different scales, or no, score. So what measure and what score on that measure. So we'll just store that into something called dat_long. So if we look at dat_long, we should now have 2 columns. One called measure, one called score. We can do view dat_long, and we see that what it's done is it's stacked up the original 3 columns. Here's all the entries for the VIQ column. Next should be the NVIQ columns, data, etc. So we've lost actually the pairing of like what person contributed what scores. But that's okay because we're just going to do histograms of these. So having converted it to long, we can do a new ggplot. Data equals dat_long. Mapping equals AES. So what do I want to put on the x-axis now? Well, yeah, I want to do histograms still.
Oh,
so score. So if I just did it like that,
it's not gonna give you the group.
Yeah, it's going to give me all the scores together. It's not going to sort of label them anyway. A nice way when you're dealing with histograms is to use the faceting to split up the plot into different variables. So facet, grid is a good one. So I want to put them so that I've got 3 different columns of data. They're arranged so I don't want any variable to specify different rows of data, but I do want different sort of left to right alignment. So that's what I'll put for measure there. So now we have the BDI histogram, the NVIQ histogram, and the VIQ histogram. One thing that's a little awry about this is that there's a lot of white space in each of these plots because each plot has the same x-axis. You can tell them to have different x-axes by saying scale equals free. And now they all have the same sort of axis, and you can get a better sense as to the relative shape rather than the location. So that's one view of the data.
What is free again? Scale?
It means that x-axis, they can just, this goes from sort of 10 to 65. This one goes from like 65 up to 140. Whereas the old one, they all went from 0 to like 150.
So what if we have one data for NVIQ like 30 or 20?
Oh, like an outlier?
Yeah.
We can talk about that in a little bit, how to handle sort of outliers. For now, this is one way of viewing the data, but we actually know that sort of for each measure, each observation in the BDI column, there's a measure, there's a corresponding sort of observation in the NVIQ, etc. So it'd be nice to see like those relationships. That's a little bit hard. You could do again using the original wide format data. You could say ggplot data equals dat. That's the original wide format data. Mapping equals AES. Put on the x-axis one of the variables, so let's say NVIQ, and put on the y-axis the other variable. And we're going to use geom points. So each dot is sort of a case, a row in that original, and we see sort of this nice scatter plot. Pretty clear that there's a relationship there. If we wanted to look at NVIQ and BDI, we could plot up that one, negative-ish relationship, and VIQ and BDI is a much stronger negative relationship. There's a package that actually I wrote called EZ, that actually has a really nice plot function in it for data exactly like this, that shows those three different plots all in one thing. It actually uses ggplot under the hood, but there's a lot going into how to produce that plot. So I'm just going to show you how to use it or show you its output. So it expects the wide format data, and it's just EasyCore. So if I run load up easy package and run EasyCore, oh, right. Dat is a tibble. It's not a data frame. EasyCore was written before Easy was written before tibbles existed, so we have to explicitly convert to a data frame. So first we convert the dat to a data frame, and then EasyCore can accept it. So there's a nice, pretty plot. On the diagonal is the... Yeah, well, it's on the thing in the diagonal. You've got the label of what variable is there. You actually get the histogram of data. Now, it's not actually a histogram. It's called a density plot. It's, imagine like a smoothed version of a histogram. So you can kind of get the sense as to like the distribution of each variable all by itself. On the lower triangle, it's got the dot plot, the scatter plot for each variable. So this plot here is the scatter plot of VIQ versus NVIQ. This plot here is VIQ versus BDI. This plot here is NVIQ and BDI. The lines just represent sort of the best fit regression through the line. Pardon me?
Is it the same as geom line?
Yeah. Well, so to get that line, you can either fit the regression elsewhere and then use geom line. There's actually a geom in ggplot called smooth, and one of the smoothers is line, or LM, linear model. Up here are the actual correlation coefficients associated with these bivariate plots. And this actually uses frequentist math to figure out whether this is a, quote, significant correlation. So any significant correlations will be pink, which they all are. Any non-significant will be a blue color, which none of them are. So
what is the definition of significant? More than 0.7?
It's a test of the slope, test of the correlation.
And what I mean is, what is the cutoff?
It depends on how many data points you have. More data points, you're allowed to see smaller. If you have lots of data, you can have relatively small correlation still be significant. So it's a statistical description, not a like a magnitude or qualitative description, not a description of like the clinical significance. Just like there's a distinction between clinical significance and statistical significance, there's a difference between like a significant correlation and a strong relationship. So usually, yeah, when you have more data, you can get statistical significance for weaker relationships. Yeah, so this is all just sort of a descriptive view of the data. We seem to have a pretty strong positive correlation between VIQ and NVIQ. Seem to have a pretty strong negative correlation between VIQ and BDI, and similarly a weaker correlation between BDI and NVIQ. But these reflect sort of point estimates in the same way that when we have data coming in, we can, for a single group, we can compute that group's mean. But that's just a point estimate for that sample mean. We want to do inference on the population from which the sample was drawn. We can say for certain that the sample mean is, say, 28 or whatever it happens to be for the given measure. But what should we believe now, given that we had some prior beliefs maybe, and we now observe this data with a mean of 28, what would be a reasonable set of beliefs for the population from which our sample was drawn? So in that same way, we observe in our sample a correlation of 0.77, then negative 0.88 and negative 0.55. We still need to do inference on what we should believe about the population that generated these data.
I'm sorry, this is essentially those numbers that it's coming out there. That's like the Pearson's R?
Yep.
That's what, okay.
Yep. So that's where Bayesian data analysis comes in and use of this Stan model. So I'll open it up. I'll also go over here and tell Stan to compile the model.
And one more question. So how much variation can we expect between Bayesian output and frequentist outputs? Like, say we do this in advance with our data and it comes out with 0.77. Are the numbers that we come up with going to be that different, or can we use this for a rough guide of whether our data analysis was actually accurate or not?
Yeah, we will encounter, so yes. Particularly in the case where a correlation, in most areas of Bayesian data analysis, if a given parameter is given a completely flat prior, the subsequent posterior, say a credible interval for that parameter, will actually have the same values as the confidence interval that you get from the frequentist tools. Most of the time we haven't used flat priors because, so for a mean, we don't want to, like, say I have flat belief from negative infinity to positive infinity. So we've been expressing normally distributed priors. That actually helps. There's a variety of mathematical reasons. It also is more reasonable conceptually. And it actually sort of helps improve your statistical power a little bit. But the correlation, on the other hand, is a value that can only go from -1 to +1. So it actually could be reasonable to express a flat prior. You can express non-flat priors, so something that sort of peaks at around 0.5 or something, or more typically something that peaks at 0 and tails off. So you have most belief and no correlation, less belief in stronger correlations. But for what we're doing today, we're going to be using flat priors. so on the correlation, so it will converge with the frequentist stuff. But I'll show you a example where, for example, dealing with an outlier, etc., that there's no equivalent tools in the frequentist toolbox. So, all right, stand model for. So I'm telling that to compile while I go over and look at it. So this should be very similar to what we had the other day when we were looking at 2 data points from the same person, time 1, time 2. And outside of stan, we converted that from time 1, time 2 to intercept and difference. Here we actually just have, instead of time 1 and time 2 for each person, or intercept and difference for each person, we've got just 3 measures. So everywhere you see k here in our model we used the other day, it had 2, but otherwise it's exactly the same. In that we're telling it we've got n people that we observed. Each person was observed k times. Well, you can put that in. Number of observations. And y is just the matrix of outcome pairs. Before it was just a 2-column matrix, intercept and difference score. Now it's going to be a 3-column matrix, VIQ, NVIQ, and BDI. But otherwise, we have a vector of means. So the first element in mu is the mean for VIQ. The second element in mu is going to be the mean for NVIQ. Third element in mu is going to be the mean for BDI. Ditto, a vector of sigmas, and a correlation matrix. Last time the correlation matrix was just a 2-dimensional correlation matrix, a 2 by 2. Now it's a k by k, so we have 3 things, so it's going to be 3 by 3. I told you this thing up here is just used to get the covariance matrix. So this is the covariance matrix. The covariance matrix is a combination of the correlation and the variability. And basically, the multinormal needs a covariance matrix as its second argument. I really wish it would make my life a lot simpler if they had a second argument where it's sigma and rho, or if they had 3 arguments instead of 2, mean, sigma, and rho instead of mean and covariance. That way it would make my code look prettier. But anyway. Otherwise, we have expression of our, well, actually, down here, we have expression of our generative model such that for each person, and we have to loop over people, so we have to say for each person, the sort of row of data for that person should be distributed as a multivariate normal, such that each column in the data set has a mean corresponding to the element of mu of that column. So the first column has a mean of mu1, second column has a mean of mu2, third column mean of mu3, and a covariance matrix of z. So the first column is going to have a standard deviation of sigma 1, second is going to have a standard deviation of sigma 2, etc. And then a correlation amongst those columns specified by rho. So it's a little annoying that I can't just go in the ideal scenario, I'd be able to say sigma and rho, and it would figure out its parameterization of the multivariate normal by itself. So you guys can just know that the model is saying there's each column has a mean, each column has a variability, and then there's a correlation amongst those columns. If you can capture that, that's all you need to know. And when you see this z bit, it's just because this particular function multinormal wants a covariance matrix, and so you have to create that by combining rho and sigma together. So that's compiled. So I need to go up here and figure out what it wants for data so I can prepare. I'll put a couple entries in my table of contents here, prep the data. So data for Stan equals list. It wants one thing called N. It wants another thing called K, and a final thing called Y. So for N, I'm just gonna, N is the number of cases, so N row that.
That's just log.
Dat is the wide version. So yeah, it's the,
Okay.
yeah, for this we want to use the wide version because it's easier. The number, K is the number of columns, so N call dat, and Y is just that. I think Stan will figure out turning that into a tibble and turning it from a tibble into a matrix. Let's see. So having prepped the data, make this go away. We can sample the model, 1, 2, 3, 4. I'll call the output from the model something called post because it has the posterior samples. And call sampling object equals mod. So I want to sample the model. Data equals data for Stan. And seed equals 1. So this is going to go a little bit slower than before. Ooh, wow. Why is it going this slow? Did I do anything? Ah, yes, okay. I know why it's going slow. These priors expect that the data coming in has been scaled. The data coming in here, I'm just giving it dat. It hasn't been scaled yet. Before I had you scale each column separately, you can actually just do that, and it's going to scale each column independently. So run that, and going faster. While that's running, I'll say that this is the bit where we're actually sort of expressing that the correlation matrix, that the correlations themselves should have a uniform distribution. I mentioned the other day that why do we have to say LKJ core? Why can't we just say like uniform 0, 1 or negative 1 to 1? That's because there are some scenarios where you can create a random sampling for the 3 correlations from negative 1 to 1 that yield an impossible scenario. So if you've got 3 things, A and B are strongly positively correlated, B and C are strongly positive correlated, A and C have to be positively strongly correlated. So there's you don't have like the possible values that the correlations can take have to be taken into consideration, and this LKJ core expresses that contingency sort of behind the scenes. So 1 in there expresses a uniform distribution across possible correlation matrices. If you want to express that you have greater belief for correlation matrices that are mostly 0, then higher values in that. So 2 would sort of have for each correlation, it would have sort of a peak around 0. The higher the number, the stronger the peak. 4 is a pretty large number. I certainly wouldn't go as high as 10. That would express like a lot of confidence that the correlations are precisely 0. So 1 is flat though. That means that we're going to get out fairly similar to frequentist for this model that the frequentists can actually do. So this is, yeah.
So that was the concern. Should we probably maybe have to use 5 to 10? Is it normally 1 plus we scale it or something?
Yeah, I don't know. You're asking under what circumstances would you choose to go that? I don't know. Um, if you have a model with lots of variables, say like 100 or so, a flat prior on all of those correlations will take a long time to sample. Um, and you'll also get sort of into issues of sort of multiple comparison, like having all those correlations, and if you're intending to kind of compare each one to zero, um, that's creates a lot of opportunity for just random chance to cause those correlations to the consequent credible intervals to exclude zero. So if you want to kind of be conservative in what you sort of would believe or would believe about non-zero with that many, then you'd start increasing the peakedness at zero, and that would have the consequence that only like really strong correlations would yield posteriors that start rejecting zero. So that's one reason I can imagine. We're just going to stick with just this one for now because we're not going to deal with those scenarios. All right, so in theory, we've got some samples that we can take a look at the summary of. So look at the summary of the posterior samples. So I'll use print, and I want to print the post object. I happen to know that there's a couple arguments that you could put in here to simplify the table. If I only want so it'll always print the mean and standard deviation for the posterior samples, but if I only want the 0.025 and the 0.975, that's the 95% credible interval, I can just tell it those probabilities. And if I only want the first two significant digits, you can say digit or digits. So the first thing I check, of course, is the R hat column. It's all ones except for this one, which is NaN, but that's one of the diagonal elements of the correlation matrix, and we can ignore anything that happens with those diagonal elements. They all should be 1, so I don't know why this one is NaN, but the others actually are 1. It's just a quirk of how they compute the thing that this column represents. And we also want to check that all the values in the NF column are greater than 1,000, and they are. These three columns, these three entries, mu1, mu2, mu3, reflect the posterior samples for the means for each column. But we've scaled it so that every column that we gave it as data had a mean of 0. So all of these should be pretty much centered on 0. Now, if we wanted to ask, okay, what should we actually believe about the unscaled data, we would have to add back in, well, multiply by the standard deviation and then add back in the mean to talk about these location parameters. We're not going to bother with that because in this scenario, we're imagining that we're not actually interested in the inference on the location, but the correlation. Similarly, we've got sigma here. This is on the scaled domain, so if we want to get the unscaled credible intervals, we'd have to multiply by the original standard deviations. So the thing that's interesting is this rho bit. And again, this is expressing a correlation matrix. So 1, 1 is the upper left column. So up here, 1, 2 is this one, 1, 3 is this one. So you can actually see the numbers actually kind of correspond in terms of what the mean of the posterior samples is. Mean of the posterior is about 7.6, 7.7 here. Mean of posterior for 1, 3 is negative 0.88 or here and 0.87 there. And to get to this one, you have to look at 2, 3, and it's negative 0.52. That's negative 0.55, so very close in terms of like the actual numbers. There is difference in that, and that's consequent to, I told you that if we had uniform on the parameters, it should come up with the same. The reason why it's different is because the Well, it actually may be partly that the mean of these these are not normally distributed distributions. But it also may be a consequence of the fact that we don't have uniform sampling on or uniform priors on the means and standard deviations. So that has a consequence that it can sometimes change the way it deals with the outlying observations. Not something I want to get into at all, though. So critically, if we look at those values, it's easiest to look at the, let's see, the 2, 3, 3, 1, 3, 2, because that's the same values, but they're all in a row there. So each of these credible intervals excludes 0. No, not 2, 3. Which set? 2, 2, 2, 3, 3, 1. This little chunk here. No.
2, 3, 3, 1.
I thought I remembered there.
1, 3.
All right. It would have to be 1 and 3, 2 and 3, but then you have to jump. Oh yeah. Okay. Yes. No, this section there isn't.
Where's 1, 2?
No, that's 3, 2. Yeah. Okay. So yeah. There's always one in the way. Okay. But credible intervals all exclude 0, so you can sort of, just like the frequentist results, where the frequentist would say these are significantly different from 0, for us we'd say these are sort of 0 is not a credible value in the posterior. So you describe the relationship as these two have a positive relationship and it's pretty strong. You can actually say, from the fact that, let me go up here, the range is from 0.67 to 0.83 as the credible interval. Those are sort of spans a range of relatively strong values for a correlation. The fact that this range goes from 0.82 to 0.91, that's a very strong correlation. And to 3, I guess this one is. And it's a sort of weaker. Yeah, exactly. So you can actually talk about the relative strength of those relationships as well. One thing that one can do in the Bayesian world that it's harder to do in the frequentist world is, right now all these distributions look relatively normal, but it's possible that there might be like outliers or something in the data itself, in which case we might want sort of to create a more robust model. So that's done here. So normal distribution has the shape that we're all sort of familiar with. We can use a different distribution, though, to express how sort of error manifests. So again, multinormal says that each variable is normally distributed with some mean and some variability, but also there's a correlation amongst the variables. We can use a different one called multi-student T. So what multi-student T does is it says each variable is sampled as a student T distribution, and there's a correlation amongst each of them. So what is a student T distribution? Does anybody happen to remember? Well, what I'll say is that there's actually another parameter in addition to the mean, variance, and correlation. There's a parameter called degrees of freedom with the student T.
Yes.
So if that parameter were really big, the student T becomes equal to the normal distribution. If you have a really small number, like 1, that means the student T has fatter tails. So I can even show you curve dt, I think it is, from equals 0. Oh no, I have to say dt x here. from equals negative 5 to equals 5. df is missing, right? Okay, so I'll say df equals 1. So that's a student t distribution. Quite a bit sort of fatter tails here than a normal distribution. It looks much more peaked in the middle.
Are the tails infinite?
Yeah, just like the normal. Yep. So let me say, and just to show you dnorm as a comparison, call equals red, add equals true. So there's, like, it pops off the screen, but there's what a normal distribution with the same mean and standard deviation parameters have should look like, and there's what the student t is. So the student t effectively says that, so for this normal distribution, a point out here would be seen as relatively anomalous, and therefore this sort of, if you imagine trying to sort of decide what standard deviation you need for a point that appears out here, you'd say, oh, this distribution actually isn't a good fit for that point, so you choose a distribution with a wider variance. Or if you just have like an outlier out here, but not one balancing it way out here, you might shift the mean towards that outlier. So that outlier is going to sort of influence the data fairly strongly. In contrast, if you use the student t, well, points out here actually are still relatively frequent. Like there's still sort of a relatively high value on this curve here. So that means that any values that appear sort of in the extremes of the data will be less influential than if you used a normal distribution.
So when you're deciding which to use, you just look at your data.
Yeah, I mean, there's not actually a strong cost to using the student t all the time. Yeah. Now, you could actually, so one suggestion is always use the student t. It costs time, like in terms of it makes the model run more slowly. But another thing you can do is, I've told you that the student t, or that the normal distribution is a special case of the student t. And I told you that you can, sort of, if you imagine this as being like a very big number, that's definitely going to be the normal. In fact, as long as you get sort of above 30-ish, it starts looking more and more normal. But low values definitely have this tailedness. You can actually estimate from your data what sort of...
How do you know if your data is normally distributed or not?
That is something, so normally distributed with some outliers versus normally distributed with no outliers is what I'm about to talk about. Normally distributed versus like log distributed, like log normal or something else, is a whole separate issue that I'm going to show you guys like in a couple weeks. That comes down to the idea of posterior predictive checks from your model. You want to make sure that your model can generate data that look like your original data. If your model assumed normality, so it had a generative model that used just normal, but the actual data weren't normal, then there are properties of the data that we can look at and compare, okay, what properties of the data that the model generates that aren't going to correspond. So like the difference between the mean and the median that the model creates versus the difference mean and median that the actual data generate reflect one property of the data that you can actually compare. Another thing is like the, we'll get into that. So that is in the general category of model checking. We've only ever so far dealt with sort of, I've been showing you models that have analogs in the frequentist world where there's just assumptions built into the model itself, and we'll talk about how to check those assumptions in, I think, a couple weeks now.
But we can check the priors, right? Because by curve to norm, we can say like
Yeah, you can just like you can use curve to see what the shape of your priors are. Um, so back to this idea that you can sort of establish a more robust approach to regression or to this correlation, um, and making sort of outlying points less influential. You could just always use a student t with degrees of freedom of 1. I think it does kind of diminish. I said that you should always use, or you could always use it. I think that there is. I would need to run some simulations to establish this, but I think there is some cost in the sense that you will have, if the data were truly normally distributed, no outliers, and you ran the normally distributed one, you'd have a narrower confidence credible interval at the end, so more power or more likelihood of saying that 0 is not very credible. Then if you again had data that's normally distributed, no outliers, but you used a fat-tailed student t, that's going to yield a broader credible interval. Because if you think about it, if I'm saying that the data points further away from the mean are sort of less influential, that's kind of like saying that you have less data in the first place. So if the data actually is informative and not outlying, it's doing the student t effectively means that you are sort of counting data near the center more as more influential than data out at the sides. But another way of thinking about that is that you like effectively have reduced the amount of data that you have. So one sort of nice way around that is to explicitly say, well, it could be normal or it could be not normal. Let's let the data decide. And so in the same way that we are letting the data decide about all these other parameters of the model, so where the mean is, what the correlations are, you can let the data decide how sort of many outliers there are, or sort of what outlierness there is, how fat are the tails of the distributions. So you could do that by, instead of just hard coding a 1 in there, you'd create a parameter. Probably want to do it like this. Vector lower equals 0, because degrees of freedom can't go below 0. It actually can't go below 1, so you'd want it lower equals 1. Call it df. And so you'd put df there. Now we'd want to put a prior on it, probably something so that we don't want to explore like DFs of like 1,000 and 10,000, because as I said, at about 30, it starts to look like a normal distribution anyway. So we probably want to express credibility that's sort of located around from 1 to about 30, and with reasonable credibility in there. So if I remember, well, I mean, if you just used like a normal distribution peaked at 1, because that's the lower bound, and then tails off with a standard deviation of, say, 30, that would be an okay one, because it sort of means that I believe that we need heavy tails as my peak belief, but I still believe that I would believe that maybe the tails aren't that heavy. So that would be one. I'll have to think a little bit more as to what the log normal would be to make it so that it sort of falls to 0 at 1, but sort of has a peak somewhere between 1 and 30. I guess this would be a scenario where I would recommend this is would be called a peaked at lower bound prior. So it's normal, its peak is at 1, and then it just falls off to towards the upper bound. I think this would be a scenario where I'd suggest that. So this would be a way of running the model so that it would adaptively trade off robustness for power. And that is a really cool way of doing things that, like, certainly the frequentist world isn't really able to do. Yeah.
For this assignment, we just use one.
Yeah. Oh, you for this assignment, I gave you this assignment anticipating that you'd seen the lecture that I gave you as a video earlier, and so I actually only for the assignment just using multi-normal is completely fine. In which case you wouldn't need that. Or, sorry. Yeah. So you want.
But
Yeah.
if we use this student T's, or like, would we get the exact same result?
Well, let's run it. Let's see. So let's do it the way that I'm suggesting. Use the df, lower equals 1. So I'm going to save that. Go back up, compile, and there's an error. Oh, I just forgot. Oh, it's not a vector. It's just a real. And it's complaining, oh, multi-normal. I didn't change that back to multi-student T. Yay. I didn't include any, I didn't add any outliers in this, so in theory it should sample more slowly but give about the same results as the version that just straight up assumed no outliers were in the data. All right, so, okay, I was a little worried that with the added parameter that had such a broad sort of space of the prior, or such a broad prior that it would take a while to sample, or take much longer to sample, but no. This is one where it probably would have benefited from making it multi-core, doing things in parallel, but I actually don't have, we got through the content faster than I needed. And we don't have enough time certainly to deal with any of the hierarchical model yet, so we'll do that next class. All right, so let's take a look at what the inferences were. And critically, I guess it's the so, I mean, oh, actually, in DF, what was that estimated as? 36 with a range of 11 to, so fairly normal as the peak, but still, let me actually just do a curve of DF of 11 or 12. So that actually does look fairly normal. Let me add the normal to that. Okay, so the lower bound of sort of its predictions of sort of the degrees of freedom that were needed, I mean, that looks really normal. So that would suggest that there wasn't any need to account for sort of outliers and be robust. So if I'd added in, presumably, this DF would drop to lower values, indicating that there were some outliers, if I added in some outliers. And the credible intervals on the correlations haven't really changed. Yep. Yeah, I mean, we have 5 minutes, or sorry, oh, More than 5 minutes, 15 minutes. Oh, great. Okay. There's one more thing that in this case of multivariate outcomes can be of interest. So this correlation table tells you like the credible intervals on each of these correlations. One extra thing that sometimes people are interested in, where's my, easy core, not actually, is, for example, what is the relationship between, what is sort of the unique relationship between NVIQ and BDI, already knowing that there's this other correlation. Now, I haven't decided whether this just is another name for the ANCOVA that I said was a bad idea. But there's a way to ask that question. What is the sort of unique relationship between these two things? When you've got a correlation matrix, there's a mathematical way to turn a correlation matrix into a partial correlation matrix. The partial correlation between VIQ and NVIQ is the amount of variability that is sort of remaining in those two variables once the correlation between BDI and NVIQ and BDI and VIQ has already been sort of removed. So ditto, the relationship, the partial correlation between NVIQ and BDI would be its relationship once the VIQ-NVIQ relationship has been accounted for and the VIQ-BDI relationship has been accounted for. So that's often of interest when you have sort of correlated data like this. You actually want to know sort of what the sort of independent relationships are. So I have a little script so it actually is a little bit complicated math to figure out, okay, given the correlation matrix, what is the partial correlation matrix?
So again, this is when people say it's been controlled for.
Yeah. So I still have to, I'll show you how to do it. I still have some reservations about it. This generally falls in the class of what might be called mediation models. So I'm going to open up my within correlations folder, open up my mediation folder. So I will add this in there. And just going to open up this quickly, copy in what I need. So there's a package that one would need to do this math, and a function that I created that I can send to you guys. That does this, and what is the last little bit? Actually, okay. So having loaded in this package and loaded in my function that I created, I now have this function get pcore from post. So it expects post as the argument there, but it's going to yield something called pcore, which is the posterior for the partial correlations. So to get the summaries of like what is the credible interval and maybe the median of the posterior correlation, or sorry, the partial correlation between VIQ and NVIQ, we want the 1, 2 cell of that. So that actually looks pretty similar to the original correlation, where it's got a peak at around 0.72. If you look at the correlation matrix, it's 7.7, and credible interval 0.62 to 0.81-ish. Ditto, the partial correlation between VIQ and BDI in this example is really strong still, even accounting for this NVIQ relationship. But this relationship, the partial correlation between NVIQ and BDI, Here, it's negative 0.55, and I can't remember what the credible interval on that was, but that's a negative 0.55. But here, for the partial correlation, we're observing that it's a positive, the credible interval is in the positive space. And we kind of could have expected that. Because if you notice, there's a nice strong negative or positive correlation between VIQ and NVIQ. There's an even stronger negative relationship between VIQ and BDI, this 0.88. But there's a weak relationship between NVIQ and BDI. So even if NVIQ just didn't have any relationship with BDI over and above its correlation with VIQ, you would have expected a nice negative 0.77-ish around there. But the fact that it's even smaller than, like it's an even weaker correlation than the original correlation with VIQ suggests that it must be the sort of variability that's extra in the relationship between NVIQ and BDI must be positive. I'm not sure if that kind of made sense. Like this, in order for this strong relationship to exist and this really strong relationship to exist, but this weak relationship to be weak, the sort of, I guess, the residuals of all these relationships must be that this is a positive relationship.
So essentially you lost VIQ's strongly negative effect.
Yeah. Yeah.
So it's not saying that it has a positive relationship, but it's saying that within
Once you've taken out
three,
this strong positive and then this strong negative, all that's left is moderate positive to create this. Now, I have to do some more thinking about, like, I feel like that's valid mathematically, but when somebody tries to then assert that NVIQ, like controlling for VIQ, NVIQ is positively related to Beck depression, I'm not sure I think that phrasing is consistent with what people like understand colloquially it means. Like you wouldn't then use NVIQ all on its own to predict BDI with a positive relationship. Like if you only had NVIQs, you wouldn't ever. So yeah, I have to think a little bit more about what that actually means. So yeah. All right. See you guys. Well, I guess in a week and a bit. Yep. I'm not sure. I'll talk to Ghislain about what to do on that Monday tutorial because I'm not going to have the assignment ready for that yet, but I might have him do a tutorial on, like, I don't know, maybe one of the R journals or R Markdown, something like that, because I think those are really cool ways of submitting assignments, for example, and reports. All right, thanks.